Let's talk about CMOS and power, and where power is burned when we have CMOS circuits. So let's take a look at this here. Here's the inverter we saw before, and the question I want you to answer is, where does the energy used to turn on this inverter go? So click on the part of the inverter here where you expect the energy that's going to turn it on goes. Well, the energy to turn it on goes into the gates and wires. And the reason we do this is we have to put the electrons in there. So if we want to turn on this circuit, maybe we'll hook it up to ground, so it's an inverter. We're going to have to put electrons all along here in order to pull the voltage down. So we're going to have to put charge on here, or move charge along there in order to change what the circuit does. So that's not just putting charge or moving charge off the gates, but it's also the wires too. Now this is for turning the circuit on. What happens when you turn the circuit on? Because we want it to do something. So if we look at what happens on the other end of it, well, usually we're going to go and we're going to hook the circuit up to something else. So say we've got it hooked up to another circuit over here. What's going to happen? Well, we've now just moved charge around on the input wires and gates to this circuit, and that's going to cause it to turn this one on. And so what's going to happen here? Well, now this circuit is going to put charge on the wires and gates that it's hooked up to, which is going to control the next one. So if you look at this, what we're doing here for the energy is we're using the energy to move these charges onto the gates and wires between circuits. So as we saw here, this gate is driving the wires and the next gate that comes out of it, and there was another gate before this one which drove that one. So where does the energy go? Well, the energy goes onto the wires and the gates that drive the next circuit. Alright, so as we saw, the energy you put into these things is stored on the gates. And it's also stored on the wires that go into that. And this allows us to get this capacitor across the gate and across the oxide here, which pulls charge in the channel and turns on the transistor. So how much energy do we need here? Well, the energy to turn on this gate is the energy for this capacitor. So it's the charge that we need to move to this gate, and the energy to charge a capacitor is 1/2 CV squared. That's just from basic physics. So this 1/2 we're going to sort of fold into the C equation here. So we're mostly going to just talk about CV squared. So this is now the energy that's on the gate. How do we get the power that's consumed by the gate? Well, the power consumed by the gate is how frequently we're putting this energy on there. So if we're pushing and pulling this energy on there 10 times a second, it's going to be that energy times 10 times per second. So it's going to be the energy times the frequency. So we take the energy that we're putting on there, multiply it by the frequency, and that's going to give us our power. Now, one thing we need to think about, this is the power if we're constantly putting charge on and off this gate. Most gates in a processor aren't used all the time. They may only be used some fraction of the time. So the way we usually do this, we have this alpha or activity factor, and we put that in there. So here's the power equation. It says it's the energy to charge up the gate times the frequency we charge it up times how much of the time we're actually changing things. So if a circuit's used a lot, this alpha is going to be close to 1. If it's used infrequently, it might be very, very small. Okay. Let's take a look at the whole picture for gate energy. We just talked about dynamic energy, but there's also static energy. So dynamic energy is the switching energy. It's the energy we use when we charge and discharge the gates and the wires. Remember, wires are a huge part of the power as well as the gates. And this is the active energy. So this is what we pay for doing something useful. So we want to do an operation. This is what actually does the operation. But there's also a whole other category here, static energy. So static energy comes from current that leaks, just going right through things. It leaks through the gate, it tunnels through the gate, and the reason for this is the gates are so thin that you get quantum tunneling these days, but it also leaks in a lot of other places. So the channel, even when it's turned off, will have some leakage. It's called subthreshold leakage. So you get a lot of leakage going on in your chip as well, and this is sort of the passive energy we pay. This is what we pay just for having the transistor hooked up. It may not be doing anything useful, but we're still going to pay this energy. Now let's take a look at how this energy breakdown is. This is from the ITS roadmap. ITRS is an industry group which puts together roadmaps, and their roadmaps are always wrong, but you can get general trends out of them. And this is looking at server power, and this is assuming we don't do radically different things. So we keep changing things as we have in the past. Let's take a look at what this says. So if we look down here in 2011, we've got the switching power for logic in green and memory in blue. So the blue and yellow and green parts here, this is the dynamic power used in memories and logic in a chip. And this yellow part here, this is the leakage power of logic, and the blue part is the leakage power of memory. Now the memory leakage is much lower because you optimize memories for lower leakage, because most of the time, most of a memory isn't doing anything. But if you look here, you see about half of the power here is going into static and half in dynamic. If you're depending on what you're targeting here, you may optimize that differently. So mobile devices try to have much lower static energy because they're not busy most of the time. An awful lot of the time they're idling and they don't want to waste lots of battery. Another thing, if you look at this roadmap, you can see this is ridiculous. If we were to follow this roadmap, they're predicting that each chip's going to use about 800 watts of power, which is absurd. The amount it would cost to cool an 800 watt processor is too much. So clearly we're not going to follow this trend. All right, so here's a question about where heat comes from. So we've talked about energy and power. So when I run this circuit, where does the heat come from? Well, the heat comes from the resistance. So there's resistance all over the place. When I'm moving this charge, these electrons through here, that means I'm going to have these electrons banging into things. That's what a resistor is. They're going to bang into stuff, and that banging in is going to transfer momentum, and that's going to mean heat transfer. So we get lots of heat from the wires that are all over the place. So obviously we have a big wire here connecting these circuits, but we've got other wires. This gate here, when we send electricity through the gate, there's going to be resistance in there. Or sorry, not through the gate, through the channel. How about the wire here which hooks up the gate? This is the source. Or down here, this wire, or this wire. In fact, almost everything in here that hooks up anything is going to have resistance. And so all these resistance are what drive heat. It's pushing the electricity through these various resistances that generates heat. Now this last answer down here was an interesting one. Is there capacitance between the source and the channel? So here's my source and here's the channel. Is there a capacitance between the two of these? And the answer is yes, there's a capacitance there, but the capacitance doesn't generate heat. In fact, there are capacitances all over the place between the source and the drain, the source and the channel, the drain and the channel, the gate and the drain, the source and the drain. All over the place there are lots of capacitance because these things overlap. These capacitances are called parasitic capacitances, and they're a real pain for analog devices because they change the frequency response, but in digital ones they basically just slow things down a little bit. So there are lots of capacitances all over the place, but they're not the main source of power. That comes from the resistance. All right, so let's summarize what we've seen from CMOS. Here are two views of CMOS. This is looking at the device, and here's a circuit. So these field effect transistors work by putting charge on the gate. The charge on the gate pulls carriers into the channel, which changes this channel here, which is an insulator, into a conductor. And that allows, if we put a voltage across the source and the drain, current to flow from the source and drain. We have two types of transistors, PMOS and NMOS, and they vary depending on how we dope here. And you can see that we use them to build circuits. So the PMOS pulls up and the NMOS pulls down. And we put them together, we can switch both ways efficiently. Where the energy comes from is when we're charging the gate. So if we want to switch the circuit, we have to put charge in here on these capacitors, and that's charge that needs to go into the wire to raise the voltage and charge on the gates as well. The power is how frequently we do this. So it's how much charge we have to move times how frequently we move it. And the heat that comes out of the device is from the resistance of moving that charge through the wires. The sort of summary of the power and energy in CMOS devices.